So now we come towards the stress. As I have explained earlier, it is force applied per unit area normal surface. Force can be taken as mg and area can be taken as area of cross section, that is pi r square or pi d square by 4. So now we come to the main concept. In equilibrium, internal reactionary force acting on a unit area of cross section of a body is called stress. In a state of equilibrium, the stress is equal to the external force applied on a unit area. If F is the external force applied on the area of cross-section A of body, then the magnitude of stress is given by function, that is stress is equal to external force applied divided by area of cross-section. So external force is F and area of cross-section is A. So force per unit area is called stress. The unit will be obviously Newton per meter square in MKS system. However, it is dyne per centimeter square in CGS system, and 1 Newton can be taken as 10 to the power 5 dynes. Dimensions will be the same as that of force and area of cross section. So for force we compute MLT minus 2, and for area of cross section we take that is L square, and then we simplify numerator and denominator. The final dimension comes to be M1 L minus 1 T minus 2. That is what the dimension of stress. So this is the dimension same for elasticity also, or Young's modulus, or we can say it is also for the Hooke's law. The stress developed in a body depends upon how the external force is applied. That is the mechanism of application of force. There are 3 types of stresses. Now, normally when we use the term 3 types, we are referring to 3 dimensions. That is variation in lengths, the area of cross section, and the volume. So the first one is called the longitudinal or linear stress. So longitudinal or linear stress means the ratio of change in length and original length. So when a deforming force is applied in the direction of length of a body, such as wire, then in this case, the force of reaction acting on a unit area of cross section of the body is called longitudinal or linear stress. Due to this, the body opposes the change in length. So now in the figure it is shown, a wire is taken, and when we speak area of cross section, we will find that the cut portion of the wire is always a circle. So original length is given as L, and when some load is suspended on the wire, it gets stretched in the downward direction, that is in the direction of force, and the change in length takes place as shown in the adjoining figure, and that will be delta L, increase in length. So normal stress is sometimes known as the tensile stress. So now we come towards the main point, that is, due to this, the body opposes the change in length. This is what indicated in longitudinal or linear stress in the diagram. Now we come towards the normal stress, and again the same figure will be applied. Normal stress means that the force is applied perpendicular to the base or perpendicular to the area of cross section. When a force is applied uniformly on the surface of a body in perpendicular direction, that is at 90 degrees, then the normal internal force acting on a unit area of surface of the body or pressure is called the normal stress. This stress opposes the change in volume of the body. So the change in volume means we are taking all the 3 dimensions simultaneously, and that is normally known as the change in volume. That is, change in volume to the original volume is called the volumetric stress. Now we come towards the tangential stress or the shearing stress. So it is clear from the figure, we have taken a cube, and for the cube, the original length is taken as L, and at tangent we will apply the force. So force is at 90 degrees to L. We are finding that if we view the left portion of the figure, we will find that the original length is L, and we find all the sides of cube, that is, there are 12 edges, 8 corners, and 4 diagonals. So when we apply force tangentially, we find that the change in length will be from E to E dash or D to D dash, and that change in length will be delta L. So that is the change in length, and original length is L. So now we come towards the main concept. When a force is applied parallel or tangential to the surface of the body, then the stress is called tangential stress or the shearing stress. That is, there is angular displacement in the site. This stress opposes the change in the shape of the body. Now we come towards strain. As it is clear from my earlier definition, that is, strain is related to that is the deformation in the body. So we will say that strain is basically the deformation in the body by the application of force. So whenever we apply some external force, body experiences some strain. So strain will be either longitudinal or superficial. You can say longitudinal strain, or it is a shearing strain, or it is a volumetric strain. So strain is defined as the ratio of the change in shape to the original shape, and if it is longitudinal, then it is defined as the ratio of change in length over original length. There will be no units. The units will cancel off in the numerator and denominator. And then we come towards the volumetric strain, that is the ratio of change in volume to the original volume. Now we come towards the main concept of the strain. When an external force is applied on the body, its length, volume, or shape changes. The ratio of the change of any dimension to its original dimension. Now, when we speak dimension, we are referring to length, area, or volume. So, original dimension is called strain. It is unitless and dimensionless quantity because from numerator and denominator, the units will cancel off. Now we come towards the longitudinal or tensile strain. As it is clear from the name, longitudinal is concerned with the length. Under the influence of the external force, the change occurred in the unit length of the body is called longitudinal strain or the tensile strain. So longitudinal strain is mathematically given as change in length over original length, that is small l over capital L. This I have already explained in the beginning of my lecture. The volumetric strain is basically related to the variation in volume. So we can say when we apply some force on the body and there is change in volume of the body, then the ratio of change in volume to the original volume is called the volumetric strain. So the main concept is under the influence of external force, the change occurred in unit volume of the body is called the volumetric strain. So the formula for the volumetric strain will be change in volume over original volume, that is small v over capital V. Now we come towards the shearing strain, and shearing strain is given by function, that is change in length over original length. So the main concept is when there is change of shape of body only, but there is no change in volume or length, then this type of strain is called the shearing strain. If a body is acted upon by an external force tangential to the surface of a body and opposite surface is being kept fixed, then the angle through which the line perpendicular to the stationary surface is turned is called the angle of shear or the shearing strain. So shearing strain is mainly concerned with the change in angle. So phi, that is the change in angle, that is ratio of the change in length to the original length. Now we see the figure. In the figure, we are taking just the front surface of a cube or a cuboid, and the length of the surface is L. And we find that when we apply force by keeping one side that is stable, if we apply force, we find that the length is slightly turned by angle phi from both the sides. So this is called shearing strain. We must know that there is a triangle formed in this, and that is a side opposite to phi will be working as perpendicular. The dotted line will work like hypotenuse, and the third line will become a base. So basically the formula is sin phi is equal to small l by capital L, because the change in angle is very small, that is phi is very small. So that's why instead of writing sin phi, we have taken phi is equal to L over L. Basically, sin phi is equal to phi when the variation in angle is very small. So either say sin phi is small l by capital L, or we will say phi is equal to small l over capital L, because sin phi is equal to phi.